So now let's look at the Gaussian mixture model in a little bit more detail. For the Gaussian mixture model, which is one specific case of the mixture modeling clustering framework that we're discussing in this lecture, we have this set up. So again, we let pi be a k-dimensional probability distribution. And now we have for each cluster, for example, the kth cluster, we have a mean mu k and a covariance sigma k, which defines the Gaussian, the multivariate Gaussian for that specific cluster. When we generate data from a Gaussian mixture model, for the ith observation, we assign it to a cluster by generating the cluster assignment IID from a discrete pi distribution. So this has not changed at all. But in the specific case of the Gaussian mixture model, when we now want to generate the observation xi, we generate it from a multivariate Gaussian using the mean picked out by Ci and using the covariance picked out by Ci. So if we define mu and sigma in boldface to be the set of means and covariances, our goal now is that given some data, we want to learn pi, mu, and sigma. So that's the inference goal. We've defined the hypothesis of how the data got to us by defining the generative model. Now that defines a joint likelihood on the data, given some parameters. And so once we have the data, our goal is now to go back and infer what are the parameters that could have generated that data. So now we have the inference problem. There are several different ways that we could do inference for the Gaussian mixture model. In this lecture, I'm just going to focus on the maximum likelihood approach. So the objective in this case is to maximize the likelihood over the model parameters pi, mu, and sigma. And we're going to treat Ci as an auxiliary data in the EM framework. So Ci, the cluster assignment, now is going to be the additional hidden data that we introduce and then do EM. So we want to integrate out Ci. Remember from the EM algorithm that we discussed last time, what that means is that we wanted to maximize the likelihood of all of the data x1 through xn given pi, mu, and sigma. And because we hypothesize that it's IID, that simplifies into a product over the individual likelihoods of each observation given the parameters of the Gaussian mixture model. But notice that there's no cluster assignment here. Ci is missing. Where did it go? We integrated it out. So Ci can be written this way, or can be brought back into the model this way, where we have the joint likelihood of the ith observation and the cluster assignment, which cluster the ith observation came from. But now we integrate, or in this case, because Ci can only take a discrete and finite number of values, we sum over all those possible values to integrate them out. So this term here, right here, is equal to this term. So if we want to know what this is, we simply write out the joint likelihood according to our model and then sum over the possible values of Ci to find what this is. So our goal now is to maximize this joint likelihood of the data given only pi, mu, and sigma, where we have summed the parameter Ci out of the model. However, it's difficult to do that. If you write out what this actually is and you take its log and you try to take the derivative with respect to pi, mu, and sigma, you'll quickly find that we're not left with a closed form solution. We can't solve it exactly. And so what we could do is we could derive a gradient method where we take the derivative and then step in that direction a little bit. But given our discussion of the EM algorithm last time, we're instead going to try to see if we can't use the cluster assignment Ci in an EM sort of framework for doing this maximum likelihood.